Okay, so this time we're going to be talking about multilinear functions or transformations or operations, whatever you want to call them. So for this, we have a different setup than for linear transformations, right? Remember that linear transformations took as input an element of a vector space, produced as output an element of another vector space. So with multilinear, we're going to have something different, which is what I have over here. The input is going to come from k different vector spaces, v sub 1 up to v sub k, right? So this is where the input comes from. The output is going to be in another vector space. They're all going to have norms because you need that. So a multilinear transformation, you have this sort of appearance, right? It takes as input a vector in v sub 1, a vector v sub 2, up to a vector v sub k, and produces output an element of w. Here I have the definition of norm, but let me first say what makes Q multilinear. Q is multilinear if, or K linear in this case, because I haven't specified a K, if it is linear in each coordinate meaning that if I fix all but one of the input vectors and I vary the other, then Q behaves as a linear transformation. Okay, what do I mean by that, right? Let me say. For any coordinate that I fix, right? So there are k input things here. So fix one of them. Choose vectors for each coordinate that's not equal to I. The function that takes, I'm going to call Q of Vj for j different from I. There's a function from Vi to W that takes, okay, let me call these V tilde j, okay? So this transformation takes as input V sub I and computes Q, or I use V tilde 1, V tilde 2, except that the ith coordinate I have this Vi, and all the other guys are fixed, right? So I'm abusing notation a little bit because maybe Vi is the first guy, right? I could be 1, I could be 2. I'm just saying, okay, at the ith coordinate you use Vi, everywhere else you use the V tilde j. Right, so since I fixed these guys, this only depends on Vi, so it's a transformation, a function from V sub I to W, and multilinear means that this is linear. So the function below is linear, meaning that if I have a sum in the input, I get a sum in the output. If I multiply by a scalar here, the scalar comes out the side of Q. Okay? So this sounds like a kind of convoluted definition, which is very appropriate because we're going to be talking about convolutions, and we're going to show that convolutions can be thought of as multilinear transformations. Let's see. So multilinear just means that I have a k that's larger than or equal to 2 here. So it's linear in several coordinates. You could put it this way. But okay, so we're going to see examples like convolutions, matrix products. Okay, let me start with matrix products, which are perhaps one of the simplest examples. And actually, let me start with an even simpler example, which is a Q from Rd times RD to R, which takes as input X and X prime and produces the dot product, the inner product, right? So we already discussed. What is this? So it's the sum of our coordinates of X sub J, X prime sub J. And this is multilinear for the following reason. If I keep X prime fixed, and if I replace X by a sum of two vectors, I can split this in two, right? So we've seen that in class already. And the same thing holds for the other coordinates. So it's linear in each one of the coordinates, each one of the inputs, sorry, as long as the other input is fixed. So this is bilinear. So it's two linear if you want. Okay, but let me notice something more general here, which maybe will help you get a better feel for what's going on. So suppose I have RD1 and RD2, and even I have some k greater than or equal to 2. And everything's mapped to R. And this is k-linear. Okay, this is kind of an abstract concept, right? So how do we understand this? So for linear transformations, we know that they correspond to matrices. Actually, linear transformations from RD to R correspond to vectors, right? Those are the linear functionals. And then we talked about them right at the beginning of our course. What about these k-linear things? How can we conceive them? Okay, that's actually not going to be too hard. So I'm going to do it I'm going to do it in the most concrete way possible. First of all, let's remember that any vector in RDI can be written as a linear combination of canonical basis vectors. What do I mean by that? I have X sub Xj sub ij, Ej, and Ej is that vector that has a 1 at the jth coordinate and zeros everywhere else. Right, so you just write it down, you see that's what you get. You've probably done that already in the linear algebra class, or hopefully you have done it already. If not, you can ask me, I guess. Okay, so suppose I compute Q. Okay, let me point out something that's slightly technical. Here I'm speaking of the canonical basis, but I actually have a different canonical basis for each RDI, and then I'm gonna represent by adding an I here on top. So E sub Ji is a canonical right? E sub 1I, E sub 2I up to E sub Dii are the canonical basis vectors for RDI. Okay, how do I compute this bilinear form or this multilinear form, right? I'm going to use linearity first in the first coordinate. And look, X sub I is a linear combination of these guys, right? So I can move the linear combination outside because this transformation is linear in the first coordinate. So I'm going to add an index here, Ji, just to and D1. And then I have X1, J1. And I have Q of the first canonical, the J1 canonical basis vector of 1, X2, X sub K. But now I can repeat that for the second coordinate because this is multilinear. So it's also linear in the second coordinate. And then I'm going to get something like this. So I get for a sum of J1 going from 1 to D1, a sum of D2 going from a 1 to D2, X1, J1, X2, J2, Q of EJ1, 1, EJ2, 2, EJK No, sorry, I'm running ahead of myself. Right, and I keep on doing that for all the coordinates, right? What do I get? I get a sum for each coordinate. I get the sum for each input, rather. And then I get a product of, and it's not a product, sorry. I'm gonna get a product right now. So I get a product of entries of x1, x2, up to xk. And I get here q, sorry, this is gonna look ej1, 1, ej sub k, k. All canonical basis vectors. So what is this telling me? This is telling me that if I have a basis, right, say the canonical basis for each RDI, I can represent my multilinear transformation in the following way. I mean, it has to have this form, right? So these guys, what are they? Well, they're just Q computed at canonical basis vectors, so these are real numbers. And given these real numbers, you can compute Q for all choices of vectors. You just have to write this thing down, right? Okay, so suppose I call these numbers by a different name, right? So this is going to be aj1 up to jk. So this is like a matrix, right? If I look at A for all possible choices of indices, so if k equals 2, I have two indices, A of j1, j2, and that's exactly a matrix. If I have k larger than 2, this is like what people call a tensor sometimes. So it's like a matrix, but except instead of having instead of being a two-dimensional table of numbers, it's a k-dimensional table of numbers, right? So you could say that it's an element of this space of d1 times d2 times d sub k, which is a space of all tables of real numbers that have k dimensions and kind of d1 rows in this direction, d2 rows in this direction, and so forth and so forth. Okay, so any multilinear or any k-linear Q corresponds to such an object, and it's easy to go the other way. So if I give you the matrix A, you can define Q via this formula. So this is very similar to what we have in matrices, which define linear transformations, except that we're writing things a slightly different way. So let me show that to you in the case k equals 2. So I'm going to erase everything and write it down. So now k equals 2. And q of x1, x2, well, I'm going to do the same thing as before. So I have x1, j1, x2, j2, and here I have q of ej1, 1, ej2, 2. And that's the same thing. You have to think a little bit as x1 dot product with the matrix A, x2, where the entries of A correspond to these guys. So A is an element of R d1, d2, d1 times d2. So I realize this can be a bit confusing, but it's mostly a matter of notation. Well, once we get going, like we start writing these things over and over again, we get used to them. But okay, my point is that, okay, two linear transformations correspond to matrices in this way, right? Two linear transformations, to make sure you understand, from RD1, RD2 to R, right? So you have R on the other side. So two linear transformations correspond to matrices in this way, and matrices are two-dimensional objects. So in order to discuss K-linear for general K, then you need to have these K-dimensional objects, which are like K-dimensional matrices, right? K-dimensional tables of real numbers. So in some sense, even though this looks abstract, it's very concrete. As we pointed out, inner products are one example. So anything of this form's an example of two linear. Actually, all examples are of this form. But there are many other examples. So let me just show to you two really quickly that we're going to discuss later. Okay. Example 3, and let me do it for k equals 2. It's two operations that I'm going to define over that space. Okay, C is C of 0, 1, R. Hopefully this space needs no introduction by now. And the two operations that take two functions as input and produce some output. And what are these operations? One of them is take two functions and compute their product. Right? So this is an operation that maps a pair of continuous functions to a continuous function. Right? We know that the product of continuous functions is continuous because if two things converge, their product converges to the limit that it should have. And convolution is different, so it gives you a new function over here, which is defined as follows. So this function computed at t is equal to the integral from 0 to t of f of s g of t minus s. And this is an operation that has all sorts of applications in analysis. Our exercises are going to hint at some of them. For instance, because when you take two continuous functions, this gives you a continuous function. That's not entirely obvious, so we have to check that at some point. But also, if one of these functions is, say, very smooth, say f is a very rigged function with a very weird graph, but g is a very smooth, nice, infinity function with lots of derivatives, then this has lots of derivatives too. So this is a smoothing operation. And it should be clear that these two things, okay, these we need to check produces always a continuous function at the output. But these two things should be clear that they are bilinear, right? So if I have f1 plus f2, I get f1 times g plus f2 times g. If I have f1 plus f2, this integral breaks in two. Multiplying by scalars, the same thing. It all works as it should. Okay, and one last example, which maybe I should have mentioned before. It's another product kind of operation. And here it is. So I'm going to call it prod 2, even though the spaces are very different. So we know that we can take matrix products, and there's a rule for them, right? I give you a matrix that has D1 rows and D2 columns, another matrix that has D2 rows and D3 columns. Then I know I can compute their product. That corresponds to the composition linear transformations, but let's not get into that. And that's going to be a matrix of D1 rows and D3 columns. And how do you write the matrix down? Well, it's you just have to say what the dead centuries are, right? So, and that is written like this. So it's like an inner product of a row of A with a column of B. And this is for J1 equals 1 up to D1, J3 equals 1 up to D3. Okay, so this is another operation that's bilinear. Well, if I have a product of more than two matrices, it would be k linear for some k. How is this bilinear? Well, the thing is, what happens if instead of A, I have A1 plus A2? Well, you have to think a little bit, but you'd have A1 plus A2 here. The sum splits into 2, and therefore the product satisfies a rule like this. And also satisfies something if I add a scalar here, I get a scalar there. And the same things hold for B, right? If B is equal to B1 plus B2, the sum splits, everything works as it should. So this is also bilinear, but over a different space. And okay, by now we have lots and lots of examples. We need a criterion to check that they're continuous, and that's precisely where the norm is going to come in. So as before, we have a definition of a norm. Before was for linear transformations, now I have multilinear transformations. And here's the definition. So I compute Q of V1 up to Vk, right? So my input space, remember, is a bunch of vector spaces. So I take one possible input, meaning one choice of little v1 and v1, little v2 and v2, little vk and vk. And that gives me the numerator, the norm of that. And the denominator, I'm going to divide by the product of the norms of the input vectors. Of course, if I want to do that, I'd have to restrict to non-zero inputs, right? All of the VI's should be non-zero. But I do that, and I take the soup of all possible choices of VI. I didn't write it here correctly, but V1 belongs to capital V1, V2 belongs to capital V2, Vk belongs to capital Vk. And that's how you define the norm of Q. So it's the same thing as for linear, except that you have more inputs, and therefore you divide by the K norms, the product of the K norms here. Okay, so the theorem is that a multilinear transformation is continuous if and only if it's bounded, meaning that its norm is finite. Except that there is a caveat, well, not a caveat, but something that we need to explain. What does it mean for a function from a product, right, Cartesian product of vector spaces to another vector space to be continuous? Okay, let's first realize that we're missing something, but that something would be easy to fix. What are we missing? So in order to talk about continuity, we need a metric. We need a way to measure distances. In the case of linear transformations, that there's really not much to be done because we had one vector space in the input, and that has a norm, and the norm gives us a metric. And of course, we have a vector space at the output, right, the counter domain, that also has a norm which gives us a metric. Now, here, we need to define a metric. We need to define a way of measuring distances in this input space, which is not one vector space. It's a Cartesian product of vector spaces. Okay, but that really isn't a problem. So let me write it over here. A remark that perhaps should stay on the screen for longer than the other things. I'm going to call this Cartesian product V. And I'm going to say it is a metric, it is a vector space. Right, so let me perhaps try to draw a dividing line here. Okay, how do I add elements here? So, right, so an element of V is a tuple, a k-tuple of one element of V1, one element of V2 up to one element of Vk. And I'm just going to define, so if I add two k-tuples like this, I'm just going to say, well, you have to make sure you add vectors in V1 with vectors in V1, vectors in V2 with vectors in V2. So that's how you define things. Right, and I actually need a little bit more space, so let me erase this bottom line here. Well, it's the same thing if you want to multiply by scalars, because if you multiply by a scalar here, you just need to multiply all coordinates by that scalar. So notice that I'm multiplying lambda v1. And okay, this defines an element operations of multiplication by scalar, sum. There's a natural zero element, which is taking v1 equal to the zero vector of capital V1, v2 equal to the capital zero vector capital V2, and so on and so forth. This is a vector space, and there's a norm on it. And that's, I mean, there are actually many norms on it that mean the same thing. One natural norm is just to say the norm of a k-tuple is the sum of the norms of the k elements. Okay, so what are we doing here? I'm saying that this space V is itself a vector space. It's not only a Cartesian product of vector spaces, but I can define a natural structure of a vector space over it. And I'm saying that I can define a norm on it as well. If each VI has a norm, then I can define a norm by just adding up the norms of the individual components. And here's the thing. This norm is in some sense related to, you remember when we defined the Euclidean norm or the LP norms over RD, right? And we said that convergence in RD means really convergence of each coordinate, right? You have the same kind of thing here. We're going to be using that later. So here's an exercise for you. Check that a sequence of elements of V converges, right? Okay, here's the exercise. Suppose I have a sequence. Okay, what's an element? I have a sequence of elements of V. So each one of these elements is a k-tuple, right? With coordinates V sub n1, V sub nk. And so Vn converges to V according to this norm, right? V is an element of capital V. If V equal to V1, Vk, and each Vni converges to Vi in the sense of the space, right? Under norm, the norm of space Vi. So this is an exercise for you. It's not a hard exercise. It's really related to what we did for RD. And that exercise is also related to the fact that there's some freedom defining this norm. I could define it as an analog of a LP norm like this. As long as P is between 1 and infinity. And I even have an analog of the infinity norm, which is just saying the norm of V sub 1 up to V sub k is the maximum norm of the VIs. Okay, so we jumped up one hurdle on our way to considering why, to proving a theorem of the sort that we have for linear transformations, a theorem that says multilinear transformation is bounded if and only if it's continuous, right? There's another thing. So what hurdle did we jump? We jumped the hurdle of saying, okay, how do I speak of continuous things if I don't know how to measure distances in this product space? Now you do. That product space is actually a vector space that has a norm. Right. Okay, so what about that? There's something else that we're going to need, which is going to be another exercise, which I'm going to write down here. So this is exercise 1 for today. Exercise 2, which is that any sequence, let me say that I have a sequence U sub n contained a new vector space with norm. And sorry, I forgot to add something. Any convergent sequence is bounded, meaning that the sup of the norms of the U sub n is finite. Okay, so this we know from the real line. we know that on the real line, if I have a convergent sequence, it's bounded. And more or less the same proof works over here. And what is that proof like? Okay, so you have these elements U1. I'm going to draw them on the real line, but really it doesn't make a difference, right? So you have U1, U2, U3, U4. Now, eventually, there's a limit here, which I'm going to call U infinity, right? The limit to the sequence. And eventually, all terms of the sequence, right? All but finitely many terms of the sequence lie in this interval. Or in this region, right? I mean, call it an interval because it's 1D, but it's in this region around U infinity. What does that mean? It means that, for instance, how do I prove that the soup is finite? Well, I take the maximum of norm of U1, U2, U3, U4, up to finitely many terms that I'll need to enter this region around U infinity. And then I say, okay, but from this point on, I can just say everybody that's close to infinity, say everybody that is within distance 1 from U infinity has a norm that's at most a norm of U infinity plus 1, right? So if I can upper bound, my upper bound is like the maximum norm of U1, U2, U3, U4, up to some UN naught minus 1, and an additional term which is a norm of U infinity plus 1, if this has width 1. Okay, that's more or less the drawing of the proof for the real line. If the proof for general vector spaces is really the same, and I think it's a nice exercise, it's not hard, and it's useful, and it's going to be useful now. Okay, so I'm going to assume that you know these exercises, or probably should, if you don't, should stop the video and try to do them before we proceed. And then we're going to prove now that this theorem that a multilinear Q is continuous in the norm. So this is the space V that we defined below, right? Real. So let me try to remove a few of these marks on the wall. Okay. You can't really tell from the video probably, but there's a kitchen sink right next to where I am, and I'm going to use some water to get rid of these whorls on the blackboard, which is actually a kitchen wall, but let's not get into that right now. Okay, it's continuous in the norm if it's bounded, and I'm going to write that we're saying the norm of Q. Really, I should write the norm of Q with all these guys, but I'm just going to say the norm of Q is finite. And that means that Q is bounded. And, okay, so that's our second last goal for the class today. So once I'm done with that, well, there are a bunch of examples that we mentioned. So multilinear transformations from our D1 or D2 to our D, matrix product to R, matrix products, product, and convolutions of continuous functions. Most of those I'm going to leave as an exercise. I'm going to go back to the case of convolutions because there's something that needs to be done. It's not as obvious or not as simple as the other cases, right? So let me mention one thing that's very important. You can use this theorem and some simple estimates to show that all multilinear transformations from RD1 times RD2 times RDK to R, or to RD, whatever, all of these multilinear transformations in finite dimensions, they have to be bounded. And the way you prove that is exactly how we prove that all linear transformations are bounded. You just look at, right, so for linear transformations, we use the matrix representation. As we mentioned, for multilinear transformations, you have this tensor representation, and that's what you use. Okay, but let me, I'm sort of circling around, let me prove this theorem for you. Right, so how do we prove it? I'm gonna first do the direction that's the most similar to what we did last time. And that is the direction of I mean, the other time we did first this direction and then the other, we're gonna do it the opposite way. Okay, if it's continuous, it has to be bounded. So it's gonna be a proof by contradiction. Assume continuous and not bounded. So remember what we did last time, right? We said that means that for all C, there exists a vector that gives a value greater than C in this ratio. And then we switch to all N. I'm gonna make things a little bit shorter this time. I'm just gonna say for all N, there exists an element of the space V, which is a Cartesian product, right? So it has this form. Such that if I look at Q of V sub n, right? So V sub n is just this K tuple, and I divide, well, it's non-zero as well, right? So all coordinates know all V and I different from 0 VI. K norm of V sub n I, VI, and this is all greater than or equal to n. Okay, what about that? As before, we're going to use this to give a contradiction, right? So, okay. And what is the contradiction like? Well, we're going to say something like, we're going to divide V sub n by something. That something should be such that, what is it called? Yeah, it should be such that if I, what am I saying? Sorry. Yeah, that something should be such that I get a sequence of vectors that goes to 0 in V, but such that Q of that sequence does not go to 0. Right, so that's what we did before. And okay, how does that work? It has to be a little bit different from before, for reasons I'm going to explain later. But the idea is still the same. So we're okay. What's the sequence, right? I'm going to define X sub n. So it's a sequence of elements of V. I'm just going to take the same thing here. So let me write it like this: Vn sub I equals 1 to k. I'm going to divide each one of these guys by its norm. And then I'm going to multiply here by some sequence epsilon sub n. And we're gonna need that epsilon sub n goes to 0. In the previous proof, we took epsilon sub n to be 1 over square root of n. But we're gonna see that we need to be slightly more careful this time with the choice. Okay, but the first thing is, I want to argue that this sequence x sub n goes to 0 when v goes to infinity. How do I do that? Well, I need to look at the norm of this guy and show that the norm goes to 0. Let me go back to the 1 norm here, in case b equals 1. How do I compute the norm of x sub n? Well, I'm multiplying by a scalar, so the scalar is going to be here. And now I need to take the sum of the norms of these guys. But notice that I always have a term like norm of v and I divided by norm of v and I. So that's going to give me 1 for each term. So this is k times epsilon n. Therefore, if epsilon n goes to 0, which I required over here, x sub n goes to 0. Now I want to compute q of x sub n and compute this norm. here I forgot the norm, right? Okay, how do I compute that, right? So I need to use multilinearity, right? Notice that here, well, okay, I could have written this like this, perhaps, to notice that I'm multiplying each term by a scalar. So when I compute q of x sub n, it's basically I have the same tuple that I have here, except that each input has been multiplied by a scalar, right? Or multiplied and divided by a scalar. So I know that q is multilinear, therefore it's linear in each coordinate. So for each coordinate, I can move its scalar outside. And okay, so what happens then? I have these k scalars, each one of them corresponding to one term in the product. So they're all going to move outside. So what I have here is q of v sub n, right? I'm also using the fact that this, okay, I should have said that epsilon n is no negative. I should have, and now I move all these scalars outside, so I get epsilon n to the k, right? I have one scalar for each coordinate. And here I divide by the product of the coordinates, of the norms of the coordinates. And this thing here is going to give me the contradiction, except that I have to be a little bit clever in my choice of epsilon. So I'm going to need a little bit more space. So if I look at this expression, it's exactly what I have here with this epsilon n to the k, right? So this thing here, q of x sub n, is greater than epsilon n to the k times n. And if you want to copy the proof that I did last time, I want this to go to infinity. Why? Because then I have a sequence of vectors going to 0, right? Those are the xn, the x sub n's. They're going to 0. But q of x sub n is not going to 0 because I have epsilon n to the k times n going to infinity. And what is the contradiction? Well, q is multilinear, right? So if I take one of these inputs to be equal to 0, the value of q has to be equal to 0, right? So for linear transformations, we know if the input is 0, then the output is 0 as well. So here, if one of the inputs is 0, that guarantees that the output is 0. So x sub n going to 0 means that q of x sub n, if q is continuous, should be going to 0 as well, right? Because q of 0 is 0, so if q is continuous, q of x sub n should be going to 0. Right. And then we have a contradiction, right? So because q of x sub n is not going to 0 if I have this, but x sub n is going to 0. But okay, why do we have to be careful? I need to make sure that I picked epsilon n in a way that ensures that these two conditions are met at the same time, that epsilon n goes to 0, but epsilon n to the k times n goes to infinity. How do I do that? Well, there are many choices. One that always works is, and I really ran out of space here, didn't I? Okay, let me just say it. You take epsilon n to be 1 over log of n. Why does that work? Well, 1 over log of n go to 0. Let's say log of n plus 1 because I don't want to deal with n equals 1 here. Log of n goes to infinity when n goes to infinity, so this goes to 0. But it goes to 0 slower than any power. Log grows slower than any power of n. So log of n to the k grows slower than n, and therefore this thing here is going to go to infinity. You can do many other things. You can take epsilon n to be 1 over n raised to some very small positive exponent, and that's also going to work. Okay, so this became a bit messy, but hopefully the idea is clear. It's the same as before. You assume q is continuous and not bounded, and you know that you have a v sub n that satisfies this, and then you just renormalize v sub n to get a sequence of vectors that goes to 0, but such that q of x sub n does not go to 0. And then you have a contradiction. By assuming that q is continuous and not bounded, you have concluded that q is not continuous. So the contradiction is that it's not possible for these two things to be true at the same time. Therefore, if q is continuous, it has to be bounded. Okay. That's part 1. And now we go to part 2. Uh, well, part two, meaning the other direction, right? The converse statement. So how do I prove that Q bounded implies Q continuous? So at this time, I'm going to need those exercises that I discussed before, um, because we're going to be talking about convergence, right? So uh, assume I have a sequence V sub n and the limiting point V, they're all contained in V. This is a bit hard to see, isn't it? So I have to write this up, if only a little bit. Proof of this direction. Assume we have a sequence V sub n going to V, and we want, right, everything here is in V, and we want to show that Q of V sub n goes to Q of V. Now, we need to write this in a way that helps us understand things, so let's notice that, well, V sub n, as we said many times before, takes the form of a k-tuple of elements, with each element being in one of the space VI's, right? So V also takes this form. And by the exercise, one of the exercises I discussed before, I know that for all I, that V sub n sub I goes to VI, right? I have this coordinate by coordinate convergence. Okay, so I also need the other exercise. So, okay, let me rewrite this thing here by saying that, I'm just going to rewrite everything here and in a kind of the form that's more amenable. I have to write this up a little bit again. Right, so what do I have to do now? I'm gonna write things differently. So I'm gonna just say straight away. I'm gonna say I have this guy, these guys, right? They're all in V. They're a sequence, and they converge to V, V1 up to V sub k. And right, so the convergence here means, well, the convergence V sub n to V means convergence of each one of these elements. And I need, right, so yeah, so now I'm not going to need this norm anymore. So let me erase this because I need more space, I think. And I'm also going to need this exercise that says that that uh, that all these guys are bounded, right? So remember that convergent sequences are bounded. So if Vn sub 1 converges to V1, it's bounded. If Vn sub k converges to Vk, it's bounded. Therefore, I can define this quantity here, M, which is just the soup of all norms here involved. Meaning, I mean, of V and I, Vi, for all I, and this is a finite number. And it's going to be very useful to know that. Okay, how do I know that M is a finite number? Well, convergent sequence is bounded, so the soup of these norms is bounded. All these are convergent sequences, so the soup of all norms are bounded. And I can take just the maximum of these soups. And then I have the norms of these guys, but just those are just finitely many terms, so yeah, the soup's bounded. Okay, now what? Now we need to, okay, so since the challenge here is, right, we have this multilinear structure and we have to use that to our advantage to consider this difference. And we need to show that this goes to zero, right? But with linear, it's easy because you put v sub n and v together inside the same Q, and then we can use the norm. Here we have to be a little bit more careful. And I'm gonna tell you what we do. So we do this. So I'm gonna try to I'm gonna write it like this. So I'm gonna build a bunch of intermediate terms between these guys. So let me say what I'm gonna call them W N K minus Q W N K minus 1. And what are these guys? So W N K, sorry, I'm gonna put the K on top here. So W and K is something of this form. So on the first coordinates, I have the coordinates of E sub n. Sorry, and this is not K, this is I. Sorry, there's a theorem about working with multilinear things with lots of indices is that the probability that you get lost with your indices approaches 1 as time goes to infinity. And it's what's going on right now. Right, so let me rewrite this. I'm going to define W and I in the following fashion. So this is a guy of this form, right? So everybody in the space V has this product form. To I and Ki. And then I'm going to say that where W and I is equal to V and W and, sorry, Ji is equal to V and J if J is less than or equal to I, and is equal to Vj if J is larger than I. So I think you can read this, though maybe not. So let me move this closer to the top. And I guess I'll have to cut this from the video. Okay, I'm gonna write this over here because it's essential. Maybe I'm not gonna cut it, and you have to get used to me doing stupid things every now and then. Okay, let me define these guys like W and K. These guys are supposed to be kind of intermediate links between Vn and V, right? So what do I mean by that? Vn I, so W and I. So I mean this, so Vn1 up to Vni, and then Vi plus 1 up to V sub k. So notice what I have over here. Up to index I have the coordinates Vn1 up to Vni. And from then on, right, so I have the inputs coming from V sub n. And from that point on, I have V, and that I'm going to define for all I going from 0 to k. But I have to be a little bit careful what I do at the extremes, right? So if I have I equals k, it means that I have Vn1, Vn2, Vn3, up to Vnk. So there's no, when I equals k, this is not there, right? So, and then Wnk is going to be equal to V sub n. when I equals 0, it means that I don't have this part. So I just have V1, V2 up to Vk, and therefore W sub nk is equal to V. Now the good thing is that when I change these terms, I'm going little by little from V to V sub n, or from V sub n to V, right? So, and I can write a telescopic sum like this. Equals 1 to k, q of W n I minus q of W n I minus 1. So it's a telescopic sum, right? So eventually, if you add everything up, the terms are going to cancel except for the term with I equals k and the term with I minus 1 equals 0, and those give you these two guys. Why is this useful? Because for multilinear things, I know what happens when I change one of the inputs. I don't know what happens when I change all of the inputs all at once. But here, in these guys, I'm changing only one input. And now let me explain to you what happens. So I have this norm. I'm just going to apply subadditivity of the norm to bound the norm of the sum by the sum of the norms. And now comes the trick, right? So look at what I have over here. I can write this guy as, now I can use linearity, right? So I'm just going to say, what happens here, right? So first look at this guy, W n I. So this guy has V sub n up to I, right? What about this guy? It has V sub n up to I minus 1. So except for this position, so let me write this guy on top here, I sub minus 1. So it's Vn minus 1 up to Vn minus and I minus 1, Vi, and then so up to, except for this position, the two guys are exactly the same. So that's what I'm going to use over here. I'm going to put V sub n 1, V sub n 2, up to V sub n I minus 1, V sub n I minus Vi, right? Those are the two different guys. And everything else, Vk. So now you can see where multilinearity comes in. I'm taking two inputs that differ in one coordinate, and I'm putting the two coordinates together here. So now what do I do with this? Well, by the definition of the sup norm, if I take the sup norm, no, sorry, of this norm of Q, if I take all Q of something and I divide by the norms of the input vectors, that can be at most the norm of Q, right? So yeah, so you can hopefully see this, and I'm just gonna write one last line over here, and that's gonna give me norm of Q times the norms of everything that's inside, but let me notice this. So the norm of Vn1 is bounded by this constant m, Vn2 the same, Vni minus 1 the same, all terms, but this guy I want to bound by m, so I get m to the k minus 1. And finally, I have this guy that's different. Okay, what's going on here? So in order to prove that Q is continuous, assuming that it's bounded, I want to show that assuming it's bounded, this thing here is going to go to 0 as n goes to infinity, right? And now what am I doing? I'm saying, okay, take this, bound by the sum of differences, and I have this expression, and I have this thing. So remember that V sub n goes to V, Therefore, v sub ni goes to vi for all I. So all of this is going to 0. Going to 0. And therefore, this thing here, well, it's sandwiched as usual between 0 and something that goes to 0. Therefore, it goes to 0 itself. And we're done. We show that when v sub n converges to v, meaning the v sub ni converges to vi for all I, then I have that q of v sub n goes to q of v, and all I needed was to assume that q is bounded. And now we're done. And given that this video is already too long, I'm going to leave convolutions and one last example of continuity for the next video.